Good morning everyone. So recall that in the last class we have discussed this term separation theorem and we talked about how to compute the normal form of a given homogeneous second order differential equation. Now we will discuss few more theorems. So the first theorem says that in the normal form, which looks like u double dash plus h of x u is equal to 0. So in the normal form, if h of x is less than 0 and if u of x is a non-trivial solution of u double dash plus h of x u is equal to 0, then u of x has at most 1 0. Yes, so interesting theorem. Let's see an example to understand what does it mean. So if I consider u double dash minus u is equal to 0, so here h of x is minus 1, which is less than 0. Yes, now what are the solutions of this one? M square minus 1 is equal to 0, that gives you m square is equal to 1, or m is equal to plus minus 1, which means that your y of x is c1 e raised to the power x plus c2 e raised to the power minus x. So both e raised to the power x and e raised to the power minus x do not have any 0, and this is why we can say from the previous theorem, from this theorem also, that it would have at most 1 0. So one theorem talks about at most 1 0, the other theorem talks about if h of x is greater than 0, for x greater than 0, and 1 to infinite h of x dx is equal to infinite, then u of x has infinitely many zeros on positive x-axis. Yes, again the example is quite simple. Now u double dash plus u is equal to 0, so h of x is equal to 1 is greater than 0, and also 1 to infinite 1 dx is equal to infinite. Therefore, if you consider any non-trivial solution which is either sin x or cos x, both have infinitely many zeros. Now we will use these theorems to have two questions. The first one says that find the normal form of the Bessel equation where p is a constant and it is greater than or equal to 0, and then use the normal form to show that the given equation, every non-trivial solution of the given equation has infinitely many zeros. So it means that we have to use this theorem. But to use this theorem, first let's talk about the normal form. So the given equation is x square y double dash plus xy dash plus x square minus p square y is equal to 0. To find the normal form, first I write down in the standard form that looks like this one, where p of x is 1 by x and q of x is x square minus p square by x square. Now the normal form is u double dash plus h of x u is equal to 0, where h of x is q minus p square by 4 minus p dash by 2. Now solve it by yourself and you realize that it comes out to be 1 plus 1 minus 4p square by 4x square. It means normal form is u double dash plus 1 plus 1 minus 4p square by 4x square u is equal to 0. Now p is strictly greater than or equal to 0. So you can see that to use the above theorem, I have to show h of x is greater than 0 and then 1 to infinite h of x dx is equal to infinite. So first let's focus on h of x. Now this h of x depends on 1 minus 4p square, because 1 is positive, 4x square is positive. It means either 1 minus 4p square is greater than 0 or 1 minus 4p square is less than or equal to 0. It means I have two cases, either p is from 0 to half or p is greater than half. Let's start with the first case. P is from 0 to half. In this case, my h of x would be 1 plus 1 minus 4p square by 4x square, and I can write it as 1 by 1 plus x square, 1 by 2 plus p, and 1 by 2 minus p. If you see h of x, then 1 is positive, 1 by x square positive, half plus p is positive, and half minus p is also positive because p is from 0 to half. So this is strictly greater than 0, even it is greater than equal to 1, which means strictly greater than 0 for all x greater than equal to 0. Also, 1 to infinite, h of x dx is 1 to infinite 1 plus 1 minus 4p square by 4x square dx. Again you will see that this term 1 after integration become x, and when we put the limit it becomes infinite. So either 1 minus 4p square by 4x square is finite or infinite, the overall integration would be infinite. It means that u of x has infinitely many zeros. Now case 2. So if I talk of the case 2, then p is greater than half. Now if you see h of x and consider p greater than half, for example 1 plus 1 minus p is equal to 1, so 1 minus 4 by 3x square, so which is 1 minus 3 by 4 x square. Depending on the x, it may be negative also. So when p is greater than half, I cannot say anything about the h of x. At least I cannot say that it is greater than 0. So in that case, I will write h of x as 1 plus 1 minus 4p square by 4x square, which is 1 by x square, and I write it as x plus root 4p square minus 1 by 2 and x minus root 4p square minus 1 by 2. Now if you see here, then this term is positive, this bracket is positive, but if you see this bracket, then we cannot say anything about it. But at the same time I can say that this whole h of x is greater than 0 if x minus root 4p square minus 1 by 2 is greater than 0. Yes, then there is no problem. So let us consider that, let denote root 4p square minus 1 by 2 as x naught. That gives you x is equal to t plus x naught. Okay, and define the new variable x is equal to t plus x naught, or x minus x naught is equal to t. Better to say like this. So this is x minus x naught is greater than 0, which you are calling it as t. Okay, now substitute all the values back. So if you substitute the values, then first change is when you are changing the independent variable from x to t. So your equation becomes d2u by dt square plus h1tu is equal to 0, where h1t, so h1t is same as h1x, h of x, because you are just substituting or replacing the variable x in terms of the t. So it will become 1 plus 1 minus 4p square divided by 4, or I can substitute here also for avoiding any confusion. So it would be 1 plus x square, x is t plus x naught whole square, then x plus x naught, so x is t plus x naught, so t plus 2x naught, and then x minus x naught, which is t, which is greater than 0 for all t greater than 0. This we have proved, for it is greater than 0 when t is greater than 0. Yes, and also h of x is same as h of t, therefore 1 to infinite h1t dt is also infinite. Yes, it means that u of t has infinitely many. It means u of t has infinitely many zeros. Now what is the difference between the zeros of u of t and u of x? So now x is equal to t plus x naught implies zeros of u of x and u of t differ by x naught, and x naught is any number. So differ by x naught, it means that they have the same amount of the zeros. They have infinite. If one has infinite number of zeros, the other also has infinite number of the zeros. And also t plus x naught. So if t is on the positive axis, t plus x naught is also on the positive x axis. It means that u of x has infinitely many zeros, and then the zeros of y of x and u of x are same. This we proved in the last class. Therefore y of x has infinitely many zeros. So very interesting question. Let's try one more question. Reduce the following equation into normal form and then find that its non-trivial solution has infinitely many zeros or not. Please do try it by yourself. So to solve it, first write it in the standard form again. So that is y double dash plus 4 by x minus 2y dash plus x square minus 6 by x minus 2 x square minus 5x plus 6y is equal to 0. Yes, it means my p of x would be 4 by x minus 2, q of x is x square minus 6 by x minus 2 x square minus 5x plus 6. Yes, so if you solve it, then normal form comes out to be, please try by yourself, u double dash. So normal form would be u double dash plus h of x u is equal to 0, where h of x is x by x minus 2 x minus 3 and y is equal to uv, where v is equal to e raised to the power minus half p dx, which comes out to be. Now the question is asking that whether its non-trivial solution is infinitely many zeros on negative x-axis. So on negative x-axis, v of x does not vanishes. Yes, so v of x does not vanishes on negative x-axis. On negative x-axis, it means zeros of u of x and y of x are same on negative x-axis. This is one thing. The other thing is that let's look at the h of x. So h of x is negative on the negative x-axis because it is x minus 2 x minus 3. So let's say if you take x is equal to minus 1, so it is minus 1, then minus 3 minus 4, so minus 1 by 12. So it means h of x is negative on negative x axis. It means if you see this theorem, recall the theorem, it says the first theorem we did in today's class. So it says that if h of x is less than 0, then u of x is at most 1 0. So h of x is negative, it means normal form, or it means u of x has at most 1 0, has at most 1 0, implies y of x has at most one. In other terms, since we have to prove does not have infinitely, I can say it has finitely many zeros on negative x-axis. So that's all from today's class. In the next class we will cover Strum comparison theorem. Thank you.